All right, yeah, thanks. I'm going to talk a bit about the broader Southeastern Soil Moisture Buildup Project, but I'll focus in the talk today on some of the low-cost opportunities that we've been developing as part of this project. As mentioned, this is part of a broader project to enhance soil moisture monitoring in the Southeast, improve applications of soil moisture. Again, for this talk, I'll be focusing specifically on the low-cost stations that we're developing and deploying alongside other sensors in the state, and the possibility and hopefully the potential for expanding this to at least to the state and potentially integrate with the broader regional networks. When we started this project, we're building off some experience from our co-I, Dr. Nair, with the Great Plains irrigation experiment. I don't know if anyone's familiar with that. There was a large amount of low-cost, kind of quick sensors developed and deployed over the Midwest to study the impacts of irrigation on the climate atmosphere interactions. With this project, we kind of started with that framework of this soil moisture sensor. You can see we used a meter Teros 10. It was a known sensor that was used within our group. It was reliable, relatively cheap, had a low power consumption, had potentially up to 10 years of deployment opportunities. We designed a custom data logger using a Raspberry Pi Zero. This was kind of version 1 essentially, and so there was a lot of issues that we ran into. One, it wasn't all that cheap because a deep cycle 12-volt battery is not cheap. That in itself is $200-300 sometimes. The power consumption was definitely to be was a bit much, and so we had to start thinking about other opportunities and ways to if we really wanted this to be low cost and rapidly deployable. Our next version, we thought we found the golden goose, if you will. This PICOM 5Pi. This chip is a asset tracker, data logger, Wi-Fi, LoRa, and narrowband IoT LTE connectivity, and it was based in Python. So this was we thought this was going to be the greatest thing, and then the great things usually don't work out. So sometimes anyway. And so it turns out these were just very glitchy. It was a kind of I guess wasn't a startup company. It was a decent company, but the cost was $70, and it just was very unreliable in connectivity. And then the actual firmware itself would go through and have some spontaneously kind of be corrupted and lose your data. And so this was about a year and a half of trying to figure out, are we doing something wrong? What's happening here? So finally, about a year and a half later, we finally settled on this asset tracker. It's called the SparkFun Asset Tracker. This is has the GNSS capabilities and the narrowband IoT. It has a SD card, plenty of hardware interfacing. It has a pretty powerful ESP32 processor, so we can interact with the sensors. So for the meter, we provide the voltage, we read the voltage back. It has it can read digital, so from our temperature sensors. And so this thing here, this little red box is about $149, and then a $15 added on ESP processor. And so that's what I'll be talking about going forward. This is kind of the new setup. We've basically have a new supposedly cheap cost version now. We've added a couple of different bicycle flags to help our cell antenna go up. We have a small 5-watt solar battery, a solar charger. We use a T-post and a PVC pipe to contain the whole apparatus. We have an undergrad who's actually an electrical engineer who helped me design the broader board and setup for this whole thing. So we have a printed board. We have room for 10 sensors. 8 of those can be analog because we have a ADC on 2 different ADCs, analog digital converters. The asset tracker itself, a clock just in case that we keep track of, so you always know what time it is in case you're not able to connect to the cell. We have backup, so if you lose cell connection, you're able to save to the SD card for as long as you have power to the system. four little lithium ion batteries. They're 3 volts, and then a solar charger. And that's the whole kit caboodle right there that we've designed. There's my undergrad student Nick Golacki who helped really did the design and printed board. And we have this is the most recent install down in the Escambia National Forest, and it's about a $600, straight up, 3 sensors across the depths and temperature, moisture and temperature. So part of this project with the Southeast Build-Out project was partnering, and we wanted to design these systems to be cheap and deployable, but we also don't want to make sure that they're somewhat quality. And so we partnered with NRCS, the scan stations, and our local NRCS to help us coordinate that. So we actually have a lot of NRCS scan sites in Alabama, more than just about every other state in the Southeast. So we were able to basically put these sensors in right next to the scan sites and evaluate them over a period of time, showing that the accuracy is pretty good. The top graph here is just the default the meter calibration suite. And then the bottom graph is if we added our own calibration over the own data. In both cases, we're in an RMSE around 3 plus or minus. So these are they're picking up the signals and pretty good accuracy alongside scan. We also did a lab analysis where we brought soil from that area and then essentially dried it out in the lab and tested it. So we got the full range from 0 to saturation. You can see pretty good results with the meter. These all line up with what's published and what the meter group says, around 3%, 2.5%, 3% RMSE. You can see, again, what we know that some of the more fine soils have difficulty in some of the reporting. And you can see this in the top graphs. This is the top 2 are the default calibrations from meter. You can see some of the more fine soils tend to basically underpredict in the super saturated realms. We can apply our own additional calibration. But it doesn't really affect the RMSE. You kind of fit a little closer to the line, but in general, it's still pretty good. So we feel pretty confident with these sensors now. So we're still evaluating this. We have a whole lot more data that we're crunching and analyzing and kind of putting together. But now we have a sensor for about $600 that we've designed. And again, it's really not the sensor itself as a meter group. All we've done is take what's very common, an asset tracker, which you probably have 6 in your car right now that are just, these things they're deployed and they're really available all over the place. So if you have a little bit of skill in being able to solder and or code in Arduino, then you can do a lot, for pretty cheap, as we've shown. One thing that I want to highlight here is by having these, we're able to really dive in and expand new partnerships because of the flexibility of having this low-cost sensor, easily deployable. And so one that I wanted to highlight here is our collaboration with the Alabama Forestry Commission. So the Forestry Commission is very interested in the role of soil moisture and live fuel and fire impacts and fire safety and fire prediction, as well as secondary fire effects. And so they see a really good partnership to better understand soil moisture in forest systems. So in lead up to a control burn that they're going to be doing in the Gulf State Park, we installed 5 sensors within the state park as a quasi-dense network. And so this is an idea to both experiment, to try to assess the ability of soil moisture to provide useful information, but it also helps us kind of, stress test the sensor itself in a somewhat dense-ish canopy understory. This sensor, it basically without solar, it'll last for about 10 days, but even just a little bit of dappled light gives just enough charge. So we're able to, the ones that we have on there are going, several, so it's been 2 months now that we've had these installed with barely dappled light. And then next week, they're actually going to light the sucker on fire. And so we're going to bury a couple of these just to see if we can keep them alive and see what happens. So it's really just it's kind of experiment just to see. We really want to understand and provide some good information for end users like the commission. These are kind of some of the data. So we use customized open source dashboards and a time series database. And this is what I was just sending to Ethan with the commission the other day. This area is actually drying out really quickly, and so we can show that in our sensors. essentially that the water table is starting to drop, the surfaces, it's no longer saturated in some of the wetlands, kind of identify when the last wetting rain was. The KBDI here went from 500 at the end of July to, so it's almost 800 right now. So they're maybe not going to burn this weekend. But this is the kind of information, like it's I think really useful. Again, we were able to just, hey, this is a good idea. All right, I've got some sensors. And so in a matter of 2 or 3 weeks, we kind of just planned this, went down with my grad student and undergrad student and installed these and are getting some interesting data that really, I think, can help showcase and provide these proof of concepts and these kind of like burgeoning, kind of case studies to really show the importance of soil moisture in a context like this. So what we're doing in the future, the plan is to utilize these to essentially build out broader monitoring technologies across the state. And so we're going to continue maintaining the current network that we have. Continue leveraging these partnerships. The Forestry Commission, there's another, the Nature Conservancy is very interested in using these for some of the ecosystem assessments that they do. And then we're planning for a broader implementation statewide. We have another, that map I showed we have 6 more stations on there now than we do when the map was made. We're trying to be strategic about the co-location of these sensors. Again, we know they're pretty good. We have 17 scan sites. We have another 9 regional CRNs. We have 3 CRNs. So we have a good network of really solid long-term monitoring stations. We want to utilize these low-cost stations to kind of supplement and provide a more dense understanding and network of soil moisture. For my role in drought monitoring and understanding, but across the spectrum. And so we're partnering with the National Weather Service with our co-ops and the COCORAs. We're basically, what I've shown here is we take a map, I put all the co-ops on there, I put all the COCORAs on there, I put everywhere we have existing soil moisture or where we plan to have existing soil moisture, and then we rank them based off proximity, based off soil type. We break the state down into the broad hydrologic soil groups. And then land cover as well, even though most of these are going to be somewhat, they're co-op sites, they're scan sites, they're probably going to be in a grassy lawn backyard. But then with the Forestry Commission, we're working really closely. That first picture I showed, that's actually right next to a raw station. So we want to put all these next to raw stations to get a better sense of what this looks like under the canopy. And so there's a lot of opportunities. And so I think that's really what I wanted to get across is we have a pretty cool sensor. I'd love to talk to you more about it. Yeah, the quick just kind of lessons learned. I'm still learning a lot. This is pretty new to me in a whole lot of ways. First thing, befriend an electrical engineer, someone who can design a circuit board, because that made all the difference in the world. It was used to be a breadboard and wires sticking everywhere. So that was a game saver. Be patient. I get really excited about stuff like this. My cart is always well before the horse. Try not to do a test sensor that you're going to have to visit, multiple times, 5 hours away. Didn't work out that great. Cell connections are just difficult. There's no way around it. This narrowband IoT, it's pretty neat technology. It's what your washing machine probably runs on. It's all over the place. It's narrowband, so it can penetrate really well. But sometimes you're just in the middle of nowhere and you don't have connection. Also, it's very cheap. The narrowband IoT, we're spending 70 cents a month right now for, I don't know, we got 15 stations, 70 cents a month. We're trying to be really, really cognizant of the analysis and trying to do really good soil analysis. We have a soils lab at the university, and so we're for sure getting characterization of the soil every time we install one. We have the capability of doing a soil water retention curve at each one. It takes a long time, but that's, it's, big goals. Again, cart way over there. But at the end of the day, like the low-cost sensors, I think they do provide some flexibility and they're easily deployable, new opportunities, useful for proof of concepts, and maybe long-term. I mean, the longest one we've had is about 1.5 years now. Granted, that's not 100% reporting, but it's been alive and, hasn't died. So that's good. It's good news. And the last thing is just, that the version control and pre-optimization. We optimize that thing over and over without trying to go back. So that's just some a few lessons that I've learned thus far, but happy to learn more and chat more, and I'm interested to hear what you guys think. That's it.
Great. Thanks very much, Lee. Very exciting. All right. Any questions for Lee?
This is very exciting. Can you host both analog and SDI 12 sensors or just analog on these boards?
As long as there's a capability to interface with a not, like proprietary logger, then we have that capability. Yeah, like the moisture sensors we have are digital. And then the analog, we actually have to have a converter to do the analog. So as long as you have an open signal that we can read digitally, it's fine.
Okay, great. Any other questions? Couple back in line, I'm getting over there. Just want to mention, we did see for those of you virtually that the speaker was coming in and out. So future speakers, try to stay steady. I probably might do it myself. Stay steady towards the mic. Hold on.
Yeah, I wanted to know how do your sensors perform in like highly conductive clay soil or salinity soil? Have you checked that out yet?
Yeah, so the several of the soils we have in North Alabama are just feels so loud. Several of the soils we have in North Alabama are very clay, like most of these, super, if not clay, like clay loams. And yeah, you can see that what we've seen is, the moisture sensor doesn't saturate all the way to what we saw in the true volumetric, but there's some calibrations that we've had, but at the end of the day, like you're still within 3 or 4%. So we feel pretty good about that, but there are ways you can further calibrate it. And we're seeing that. And the more coarse soils, it performs better. The finer, the clayier the soils, it starts to degrade a little bit.
Okay, we've got a question online. Can you comment on maintenance frequency, site visits of these systems?
Good question. At first it was, it felt like it was weekly, trying to figure the things out. But at this point, and so again, I want to stress this was not from the beginning, but at this point with the final sensor that we have, we're still testing these, but they are 2 months without having to, we're now measuring the voltage and the solar, incoming solar, the voltage of the battery, so we can kind of understand if things are going haywire. But hopefully the idea would be every 6 months, kind of give it a check.